My name is Anil Seth. I'm Professor of Cognitive and Computational Neuroscience at the University of Sussex in the UK. And today I'm going to be talking about consciousness in humans and in other things too. So consciousness is one of these topics that's simultaneously a very deep scientific and philosophical mystery, but it's also something that we are all intimately familiar with in everyday life. We all know what consciousness is because we know what it's like to lose it. When we fall into a dreamless sleep, consciousness goes away and it returns when we start dreaming or when we wake up. Consciousness is lost even more profoundly in conditions like general anesthesia, which really turn us conscious creatures into objects, and then, fortunately, back again into people when the anesthesia wears off. And during that period of anesthesia, consciousness is completely abolished. That any amount of time could have passed for people under anesthesia. It's oblivion, which is the complete absence of consciousness. And when we are conscious, we're all familiar with what being conscious is like. When we open our eyes, our brains don't merely process information. There's a whole different dimension. We have experiences. This is a photo of the sea near Brighton, where I live, from a few weeks ago. And when I'm down by the beach and I open my eyes, I have experiences of the colors, the silvery colors of the sky and the sea. And I hear the sound of the waves and feel the breeze on my face. We have experience. We don't just process information. And as well as experiencing the world around us, there's also the experience of being a self within that world, the specific experience of being you, or being me, or being any of us. And it's this aspect of consciousness that I think most of us cling to most tightly, the experience of being the individual that we are. It's what gives our life meaning, joy, but also sometimes suffering and pain too. That's what consciousness is, intuitively. And a more formal definition, and some of the definition I quite like working with, comes from the philosopher Thomas Nagel. And Thomas Nagel said long time ago, 50 years ago now, an organism has conscious mental states if and only if there is something it is like to be that organism. And what he means by this, I think, is that it feels like something to be me. It feels like something to be each one of you listening. It probably feels like something to be a bat, although only a bat will know what that feels like. Probably feels like something to be an elephant and kangaroo and maybe a fish. But it probably doesn't feel like anything to be a table or a chair or a laptop computer or an iPhone. For these things, they may do complicated things, certainly my computer does, but there is nothing it is like for the computer to be a computer. There is no experiencing going on. That, for me, is the simplest and most useful way to think about what consciousness is. And it's useful because it emphasizes what consciousness is not. Consciousness is not the same thing as intelligence. It's not the same thing as having language. It's not the same thing as being a self in a particular, having an explicit sense of identity. It's not the same as behaving in any particular way. It's simply the raw fact that experiencing is going on for that system. So with that definition comes the question, the big question, or as the philosopher David Chalmers put it, the hard problem. Why should physical processing give rise to a rich inner life at all? It seems objectively unreasonable that it should, and yet it does. On the one hand, we have the brain. It's a very complicated object. It's made out of brain cells and other stuff, and there are about 86 billion brain cells, roughly, and 1,000 times more connections. Extremely complicated, but it's stuff. And on the other hand, we have consciousness, conscious experiences, the redness of red, the sharpness of pain. And how we explain one in terms of the other has been a challenge that has flummoxed philosophers and scientists for thousands of years. Descartes, hundreds of years ago, struggled with this and probably invented the problem as we see it now by cleaving the universe into two parts, res cogitans on the one hand, the stuff of mind, the stuff of consciousness, and res extensa on the other hand, the stuff of the physical world, spatially extended matter, and how the two relate has remained a thorny issue ever since. Put like this, the hard problem seems to resist any kind of simple or even complex solution in terms of science. Many people have argued that conscious experiences just aren't the kinds of things that science as we have it can account for. And this has led to claims that consciousness is beyond the reach of science. But I don't think this is true at all. In fact, and I'm not alone in this, there's a very thriving neuroscience and science in general of consciousness. Now, an alternative way to think about how to approach and make progress on the problem of consciousness is what I've come to call the real problem. And it's not a new way of thinking. It's what a lot of people in the neuroscience of consciousness tend to do. And the real problem is simply this. How can mechanisms and processes in the brain and the body explain, predict, and control properties of consciousness, functional and phenomenological? What does this mean? It means that instead of trying to address this one big scary problem of how consciousness happens and look for one eureka moment of a solution, rather recognize that consciousness exists, recognize its intimate dependence on the brain and the body, and ask the questions that science usually asks. How can we explain why particular conscious experiences are the way they are in terms of the underlying brain mechanisms? Can we predict when particular conscious experiences will happen? And can we ideally control them? And the properties of consciousness here are things like why experiences are the way they are and not otherwise. Why is emotion different from vision, let's say? What happens under sleep and anesthesia? And there are both functional properties, what we can do in virtue of being conscious, the benefits it gives us as an organism in the world, and also phenomenological, the experiential properties of consciousness. Again, why is vision, why does it feel the way it does compared to emotion or smell or something else? And in this way, the idea is that we chip away at the hard problem of consciousness, dissolving it rather than solving it, until eventually, the hope is, it disappears in a puff of metaphysical smoke. Now, there's a historical precedent for thinking this way, which is worth bearing in mind. And that's how scientists have come to understand life. It wasn't so long ago, maybe 150 years ago, that physicists and chemists and scientists of the day thought that life could not be explained in terms of physics and chemistry, in terms of stuff. There had to be, the suspicion was, something else, some special source, an élan vital, a spark of life that would explain the difference between the living and the non-living. There was a hard problem of life, as there is a hard problem of consciousness now. But instead of finding the spark of life, or worse, claiming that life somehow doesn't exist, then biologists of the day and physicists and chemists just got on with the job of recognizing that life has many properties and explaining those properties one by one, things like homeostasis, metabolism, reproduction, so on. And as they did this, life became a little bit less mysterious. Now, we don't understand everything about life, but there's no longer a sense that we need to appeal to something supernatural, something beyond the resources of science as we know it. The hard problem of life wasn't solved, it was dissolved. And so perhaps the same thing will happen for consciousness. As we understand more about its properties and how to relate them in an explanatory and predictive way to the brain and the body, the sense of mystery sort of surrounding how consciousness happens will also begin to dissolve and fade away. There's one other very useful historical angle here, which is physics itself. Physicists have made great strides in explaining properties of the universe and making very precise predictions, but they still haven't told us why there's a universe in the first place to explain. So let's ask from science what science is capable of doing and judge its progress by that. Okay, with that in mind, I want to flesh out this promise a little bit by discussing a couple of different ways in which we can make progress. So thinking about consciousness not as a single big scary mystery, but as a collection of related properties. There's many ways to think about this. In my own work, I like to divide consciousness roughly into three different areas. There's conscious level, how conscious you are on a scale from being completely unconscious, as in general anesthesia and pathological states like coma, to being asleep, to being wide awake as we are now, and perhaps other global states like the psychedelic state or the hypnotic state or something like that. That's conscious level. Then there's conscious content, which is the specific conscious scenes that we have when we are conscious. Those elements, the sights, sounds, colors, and shapes, and people, and places, and objects that populate our conscious experiences when we are conscious, the experience of a world, very simply. And then the third aspect, which is a subset of conscious content, but the key subset is this experience of being a self, the experience of being you, which is itself complicated. There are experiences of the body, there are experiences of personal identity, and so on. So today, I'm going to not talk about conscious level for reasons of time, but I want to focus on conscious content and conscious self. And there's one key idea that helps us understand conscious experiences of the world around us and of the self within it, which is that your brain, my brain too, your brain is a prediction machine, and that what you hear, what you feel, what you smell, what you see are nothing but the brain's best guesses, the brain's predictions about what's out there in the world or in here in the body. This is the idea we'll use to build these explanatory bridges between neural circuitry and the properties of conscious experience. Now, this is not a new idea at all. It goes back as far as you like in philosophy and in science. In philosophy, you can go back all the way to Plato and his allegory of the cave. Now, in Plato's allegory of the cave, you have prisoners who are chained to the wall of the cave, and all they have access to are shadows cast on the wall of the cave by firelight. And the prisoners in the cave take these shadows to be the real world, because that's all they have access to. And now, so basically these prisoners in this allegory, I mean, they're treating what they see indirectly as a real reflection of what's there. Now, if we fast forward over a couple of thousand years to the present day, instead of prisoners trapped within a cave, inferring the world through shadows, imagine that you are your brain trapped inside the bony vault of the skull. No prisoners, it's the brain. Now, just like the prisoners in the cave, there's no direct access to the outside world. All the brain has to go on are signals, sensory electrical signals, which are noisy and uncertain and ambiguous and only indirectly related to how the world really is, to what's really out there. So to make sense of these signals, which are also unlabeled, sensory signals do not come with labels on, like I'm from a cup of coffee, or I'm from a cat, or I'm from a table. They don't even come with labels about which sensory modality they reflect. They're just electrical signals. So to make sense of them and to figure out what's out there in the world, the brain has to combine these sensory signals with its prior expectations or best guesses about the way the world is. And the sensory signals are then used to update and calibrate these best guesses. So this is the core idea. What we experience is not a readout of sensory signals, but it's the brain's best guess about what's out there, which is created by combining the brain's prior expectations about the way the world is with these noisy and ambiguous sensory signals. That's the key idea. Let me give you a couple of examples of how this happens in practice. This is a well-known visual illusion called Adelson's checkerboard, and you may well have seen this before. In Adelson's checkerboard, there are two patches labeled A and B here. And when I look at this image, and when I think basically everybody else looks at this image, the two patches appear to be different shades of gray. But of course, this is an illusion. They are not different shades of gray. They are in fact exactly the same shade of gray, as you can see in the second image I put up, where the two patches are joined together by a bar of continuous gray. Now, if you think there's some kind of cheating going on, well, this isn't true. If I just move this bar across, you can see there's really only one shade of gray here. Take it away, and they look different again. So what's happening here? Well, what's happening here is that the brain has knowledge encoded deep within the circuits of its visual cortex, your brain too, that objects under shadow appear darker than they really are. So as a result, when the brain is trying to make sense of the sensory signals, we experience the patch B as lighter than it really is. And the checkerboard context helps frame that expectation too. So what we see is not what's actually there, but it's the brain's best guess of what's there, which is a checkerboard. Let me give you one other example. This is another of my favorite illusions. This is called the hollow mask illusion. Now, every face that you've ever seen and that your ancestors stretching back many millennia have ever seen has pointed outwards, well, unless you've seen a mask before. And faces are very, very important things for human beings. Our brains are well tuned to pay attention to faces, to recognize them, to recognize emotional expressions and so on. And so the brain has very strong prior expectations about what faces are like. And one of the strongest parts of this expectation is that faces point outwards. And this expectation is so strong that when the sensory input is coming from a hollow face that's rotating, the brain would rather reach a conclusion that there's a face rotating in two different directions at once, which I hope you can see, rather than that it's a upside out, well, an inside out hollow mask. Again, this is showing how the brain's expectations can really shape what we experience. So those are some nice informal examples. More formally, what the brain is doing here can be understood in terms of a very famous theorem in mathematics called Bayes' theorem. Now, Bayes' theorem is simply a way of optimally reasoning when things are probabilistic. It's a way to combine, to put it another way, Bayes' rule, which is this equation at the top, tells us in general how any system should combine what it already knows, which is called the prior, it's PA here, with incoming sensory information, with new information, basically, which is at the top, the likelihood, to update what you should now think. Basically, what should I think next, given what I already know and what I am now learning when things are all uncertain? Now, on the bottom, you can see this represented graphically. There's the prior belief, what I know now, and it's a curve, so it's spread out over a range of possibilities with a peak at the most likely. Then there's a likelihood, the sensory data, in the case of perception. And when you combine these two curves, you get the posterior, what I should believe now, given what I knew before and the new information. Now, that's just a framework for thinking about how the brain does perception in terms of it has expectations about what's out there, and it uses new sensory information to come up with a new best guess of what's going on. The first person, to my knowledge, to really propose that the brain was approximating this process somehow while doing in the service of perception was Hermann von Helmholtz, a German physicist and physiologist, who came up with the idea that the brain is engaged in a process of unconscious inference. So it's doing something like Bayesian inference under the hood, and what we consciously perceive is a result of that. And that was a real starting gun for thinking about perception in this way. And it's quite a different way of thinking about perception. Now, many textbooks on how visual systems or perceptual systems work, you'll see pictures like this. This is the monkey visual system. And in the sort of standard view of perception, things happen in a more or less outside in or bottom up direction, in which information streams into the brain from the outside world. And features of increasing complexity are picked out from this stream, fished out from this stream as it gets deeper and deeper into the brain. So simple features like this patch of oriented lines, that happens early in early visual cortex, and then more complex features like parts of faces or entire objects are picked out deeper and deeper into the brain. Now, there may be some sort of top-down or inside-out modulation, but in this view, the brain is reading out the world in this outside-in direction. That's kind of the how things seem view as well. It may seem to each of us that the world is just there, and we absorb it kind of directly into our minds through the transparent windows of our eyes and our ears and our other senses. It might be intuitive to think of things this way, but the idea of the predictive brain and predictive perception changes things around completely. Now, instead of the sensory signals being read out to form like an internal model representation of the world, rather what's going on is the brain is always making predictions about the causes of the sensory signals that it gets based on a model, a generative model of the causal structure of the world and the body. It's always making predictions, the green arrows here, and using the red arrows, the sensory signals, to calibrate these predictions, to keep them tied to the world and the body in ways that are not guaranteed to be accurate, but in ways that are useful for the brain in controlling behavior and keeping the body alive. And the idea is by doing this continual dance, this reciprocal exchange of prediction, top-down prediction and bottom-up prediction error, the brain is able to approximate this process of Bayesian inference. This is a mechanism by which the brain can do an approximation to Bayesian inference on the causes of sensory signals. From the point of view of consciousness, the key claim here, and this is the claim that I make, the hypothesis that I'm trying to test or that's guiding my work in all sorts of ways, is that what we experience, the perceptual content that we have, is conveyed by the top-down predictions, with the bottom-up sensory signals just conveying or primarily conveying the prediction errors. This is the counterintuitive bit. Even though it seems as though we just register the world as it is, in the prediction machine view, we actively construct our experienced worlds. The world that we experience is a kind of neural fantasy that is constrained by, controlled by, calibrated by sensory signals from the world. We experience it in an outside-in rather than inside-out direction. That's the idea. Now, there's a ton of different experiments that flesh out this idea. There's certainly not proven. This is not something that is even really the consensus view, but I think it's a very powerful framework, and there are many experiments that fit very well with it. One of them, I'll just give you an example. It's an experiment we did in my group nearly 10 years ago with Yaya Pinto, who was a postdoc at the time. And what we did here was we used a technique called continuous flash suppression, which is a method where you show one image to one eye, let's say a face, and this image starts off at 0 contrast and gradually gets more and more contrasty. And in the other eye, we show a changing pattern of colored blobs, which starts off high contrast and then fades out. Now, when people have this situation, we use a stereoscope to split the image. People initially see the high contrast changing shapes, and at some point, the image will break through, and that's what they will perceive. You never perceive this kind of mix, or you rarely perceive a mix of both. You tend to see one and then the other. And what we also did in this experiment was we manipulated what people would expect. We gave them a word. You can see the word either face or another word like house. And these predictions could be either valid or invalid. So sometimes the word face was followed by a face, but sometimes the word face was followed by an image of something else, a house. And what we were interested in was how quickly the image broke through into people's conscious awareness And to cut a long story short, what we found over many experiments was that valid expectations accelerated conscious perception. That's to say, people saw more quickly and more accurately that which they expected to see compared to what they did not expect to see. Now, we often say, in English anyway, that I'll believe it when I see it. But this experiment and experiments like it suggest that maybe we should say it the other way around, that I'll see it when my brain believes it. So this is one experiment just quantifying a little bit that the brain's predictions really do make a difference to conscious perception. Another experiment which actually follows on, although nearly 10 years later from that first experiment, led in this case by Marta Otten, also with Yaya Pinto, we showed the same effect applies to our recent memory as well. So in this experiment, we used a slightly different design where we had letters that were either the normal way around or that there were mirror images of letters, so they looked wrong. And we asked people to select letters that had changed when we showed two separate arrays of letters. And we asked people basically also to tell us how sure they are about their decision. And again, to cut a long story short, what we found over a number of different experiments again, is that over a period of only just a few seconds, people's short-term memory of what they think they've seen starts to change from what they actually saw, what was presented, to what they might have expected to be there. In other words, people's responses became more dominated by right way round letters, which are expected, compared to mirror image letters, which are statistically unexpected, as you go back in time. So memory also is not a faithful record of what we experience. Our memories become distorted and corrupted over time by brain statistical expectations of how things are. Now, this may not be a bad thing. Memories may be more useful if they, over time, conform to expectations. But it's certainly an effect that is very experimentally noticeable. Now, just a quick sidebar here to put some of this in a wider context. I've been talking about the brain as a prediction machine and this predictive idea of conscious perception. This is one among a number of different theories of consciousness. A couple of years ago, the philosopher Tim Bain and I collected a review of different theories of consciousness, and they fall into roughly 4 groups. There are these predictive processing or re-entry theories, it's the bottom right corner. What I'm talking about is a version of those. There are also other theories, such as global workspace theories, integrated information theories, and higher order thought theories. And these all try to explain different aspects of consciousness, and they make different assumptions. So they're actually very hard to compare against each other, even though a lot of effort is currently going into trying to do just that. But I just wanted to give a sense of the wider context here. I won't go into these different theories, but there are other options available, and they're all interesting and rich in their own ways. In fact, there are many more theories than just these 4. This is a table from the paper. We found more than 20, I think, distinct theories of consciousness that all make different assumptions and have different explanatory targets. And it's a current priority to try to winnow down, reduce down this space of theories that we have, so that we have fewer but stronger candidates. Back to the idea of the brain as a prediction machine. This concept can also help us understand aspects of conscious experience that depart from the usual. When we start to see things in an unusual way, or hear things, or feel things. A question to ask here is, what would we experience when the brain's predictions are overly strong, so they start overwhelming sensory data? Faces, again, are a good context to explore this idea. We've all seen faces in clouds, or even faces in the sides of buildings. This, again, is because faces are very, very important stimuli for us human beings. So it's as if the brain is continuously projecting predictions of face out there into the incoming river of sensory information to see where it catches. And when it does, we experience little echoes, ghosts of faces, even where there is no actual face to be perceived. So using this phenomenon, it's called pareidolia, which means seeing patterns in things. Using this as a starting point, we, in my group a few years ago, we wanted to understand what would happen to model more specifically what would happen in this situation, overly strong perceptual predictions. So to do that, we took a neural network. This is one of the classic old visual neural networks called AlexNet, which is able to identify with pretty good accuracy what objects are in images. And it all works in the bottom-up direction. You show the network an image, activity flows up through the network, and you get an answer. But what we can do, what Google did as well, we based our work on theirs, you can run it in the other direction, and you can basically give the network an image or even just some random visual snow, and you fix the output and then push activity back down through the network in the other direction from the top down and update the image until the network settles into a stable state. So this is, I mean, it's a very brute force way of modeling what would happen if the brain's predictions are dominating the sensory data. At least it's the first way of doing that. When we did this in our first study, we developed this algorithm or adapted it from Google's work, and then we applied it to every frame of a panoramic video that we'd taken at Sussex University. And then people would put on a virtual reality headset and look around and experience this panoramic video. And it's much better in the headset itself, but you can get a kind of idea what's going on here. And there are a few too many dogs here. This is not how Sussex campus normally appears. It's sort of like a psychedelic experience, but not really. And what's critical here is that this computational model is not modeling a particular kind of behavior. It's modeling an experience. It's a model of a particular kind of phenomenology. Nothing specifically, it's a proof of principle, proof of concept. What we've done since then is try to get more specific about these things and develop specific computational models of, in this case, different kinds of visual hallucination. Hallucinations that appear in Parkinson's disease, which can be very rich and complex. Hallucinations that appear after visual loss in Charles-Bonnet syndrome. And hallucinations after psychedelics or during psychedelics, which have a different character. Again, they can be transformations of sensory input and have complex geometries and things like that. So by adapting the neural network approach that we had, we're now able to model specific kinds of visual hallucinations and then go to people who have these experiences and ask them to validate the models by telling us, is this close to what you actually experience? And we can close the loop that way. And this becomes, I think, a powerful way of understanding the potential neural basis of altered visual perception and therefore also normal visual perception too. This paper just came out in 2024, models of these kinds of hallucinations. So stepping back, there's take-home message from all this, which is if we can think about hallucination as a kind of uncontrolled perception in which the brain's best guesses have lost their grip on reality, well, then we can also think about perception in the here and now as also being a kind of hallucination, but in this case, a controlled hallucination in which the brain's best guesses are reined in by, controlled by, calibrated by the real world. I think that's a very useful way to think because it underlines this continuity between hallucination and normal perception and emphasizes that all of our perceptual experiences are driven by the brain's predictions about what's going on. We experience the world from the inside out just as much, if not more, than from the outside in. Now, there's one implication of this I want to draw out before moving on to the self, which is nicely put by the novelist Anais Nin. We do not see things as they are, we see them as we are. And we are, of course, all different. Now, we're very used to this from the outside. We're all different heights, body shapes, skin colors, different fashion choices, all of these kinds of things. There's an external diversity to humanity, which is increasingly recognized and increasingly celebrated. But diversity on the inside is much harder to recognize and therefore much harder to celebrate too. But just as we are different in our body shapes, we're also all different in our brain structure, in the fine details of our brain architecture. But no, nobody sees that. And the world of my experience is my experience alone. I can't directly perceive what's going on in anybody else's brain. So I think we radically underestimate the amount of perceptual diversity that's out there in the literature, so out there in the world. Now, sometimes it does become clear. One of my favorite examples is this image of a dress which tore through the internet about 10 years ago. Now, half of the world seemed to see this dress as blue and black, and the other half of the world seemed to see this dress as white and gold. I see it as blue and black, by the way. What's interesting here is not only that people could see the same image so dramatically differently, and this has to do, by the way, with the process of color constancy. Like, it's not clear in this image what the ambient light condition is. So it seems that some people's brains assume that it's a bluish outside lighting, and other people's brains assume that it's somehow a yellowish indoor type lighting. And so we see different colors. What's really interesting to me about this is the conviction with which people held their own way of seeing, to the extent that you really couldn't understand how or why anybody could have a different experience. I think this is very telling, that because our perceptual experience seems to be a direct window onto the way things are, it's very, very hard for us to appreciate that other people might be having a different experience, even for the same shared objective reality. Now, the dress came and went. The other main point here is that this diversity of our inner experience is not just a quirk that happens in examples like this. It's happening everywhere and all the time. It's just that most of the time we don't really notice it. This is because the differences might not be so dramatic, that they show up in our language or behavior. And again, because we seem to see things as they actually are. Our perception has this property of phenomenal, naive realism. Now, in an attempt to try and understand more about this inner diversity, we recently started, and we're halfway through a project called the Perception Census, which is a large-scale citizen science project trying to map out how our inner worlds differ along many different dimensions at once. Now, there's a lot of psychology studies out there that look at individual differences in perception, but they typically focus on just one or two dimensions at a time. What we wanted to do here was look at many, many different dimensions of perception at the same time: sound and music, time, vision, the effect of expectations, color, and so on. And so we created, in collaboration with Glasgow and Collective Act, a online set of questionnaires and experiments that people could do. We've finished data collection now. We haven't finished analysis yet. People could do this, and it took quite a lot of time. If people went all the way through, it'd take them more than 2 or 3 hours. So we have a lot of unique data. We had about 35,000 participants from over 100 countries taking part. And this promises to give us a unique window into perceptual diversity, how we each experience a different world. And one other thing just to notice here is I'm using the word perceptual diversity rather than neurodiversity for a very specific reason. Neurodiversity also emphasizes that we all differ, but in practice, neurodiversity has become associated with neurodivergent conditions like autism in particular, but other things too, like ADHD. And ironically, that use in practice has reinforced the wrong idea that if you're not neurodivergent in a specific way, then you're neurotypical and see things as they are. So I wanted to use a different word to get across that we all see things differently, even if those differences aren't very large. I think that's critical to understanding our inner worlds. And there's another reason to recognize and to examine perceptual diversity, which is that it's probably a very valuable thing. We're all used to the idea now that biodiversity is super important to have rich and healthy and resilient ecosystems. And it may very well be that to have rich and resilient societies, we need a diversity of minds and a diversity of ways of seeing, ways of perceiving as well. In the last part of the talk, I want to move on from conscious content and talk about conscious self, the specific experience of being you or being me. Now, there's one way to think about the self, which might be the most intuitive way, which is the following. There's a world out there. The brain does this business of perceiving the world, in this case, through this top-down best guessing. Then the self is the thing doing the perceiving, that's perched inside the skull somewhere, peering out at the world through the windows of the eyes, deciding what to do next, then doing it, making some action. The world changes, and round we go. We sense, we think, we act. That might be how things seem, but it's not how things are. And the idea here is that both our experiences of the world and experiences of the self are kinds of perception, are controlled hallucinations, brain-based best guesses. The same principle underlies both kinds of conscious experience. The first indication that something like this is a useful way to think is that there is not just one thing it is to be a self. There's no single essence of you or me that is indivisible, immutable, and sort of yes, a singular. In fact, there are many different ways that we each experience being a self, human self. There's the bodily self, which is the experience of being and having this particular object, which is the body. Then there's the perspectival self, the experience of perceiving the world from a particular first-person point of view, usually somewhere behind the eyes. Then there's the volitional self, the experience of being the cause of actions, the author of one's own thoughts, the sense of free will, we sometimes call it. Then there's the narrative self, the experience of being a persisting identity over time with a set of memories and plans for the future. And then finally, there's the social self, that aspect of what it is to be each of us that is refracted through the minds of others. Part of what it is to be me is the experience of perceiving what others perceive about me. Myself is literally distributed in the minds of others. So I just want to focus today a little bit on the bodily self, the experience of being and having a body. And the lesson is much the same, that these experiences are not direct readouts of the way the body is, but they are brain-based best guesses, controlled hallucinations. But now the sensory signals come not from the world, but from the body itself largely. There's a very good example of this, a classic illustration, something called the rubber hand illusion. And this illustrates just how changeable, how malleable our experiences of what the body is are. Now, in the rubber hand illusion, there's a participant, the guy in blue, and his real hand is hidden from sight behind this cardboard partition. There's a fake rubber hand placed in front of him. And then the experimenter with the green shirt takes 2 paintbrushes and strokes both the rubber hand and the real hand in synchrony, while the guy in blue is looking at the rubber hand. Now, the idea is that from the perspective of the brain of the guy in blue, it can see a hand. It's roughly where a hand ought to be. It's seeing the fake hand be touched, and it's feeling touch because the real hand is being touched at the same time. So the idea is the brain's best guess in this case is, well, I know it's not my hand, but all these other things line up, so I guess it's kind of my hand. And you have, as a result, the experience of ownership over, or partial ownership over, this rubber hand. It somehow seems to be part of the body, even though you know it isn't. There are many ways to test how the rubber hand illusion works for a given person. My favorite way to test it is by using a fork like this. You can see the guy really reacts as if it's very clear from this illustration that he was anticipating some kind of pain as the fork came down. So this shows, I think, very beautifully how we can't take our experience of what the body is for granted. And there are many clinical conditions which actually are much stronger than this, where people experience limbs that are not there, like in phantom limb syndrome, or experience their existing limbs as not belonging to them, as happens in a condition called somatoparaphrenia, or more generally xenomelia. Now, back to the rubber hand illusion. One thing about the rubber hand illusion is that it happens differently for different people. Some people experience it very strongly, other people not so much. To understand a bit more about this, Peter Lush, a postdoc of mine at Sussex, long-term colleague as well, did the world's largest rubber hand illusion study with over 350 participants to look at individual differences. What explains why some people experience it strongly and others don't? So we did the rubber hand illusion on this large collection of people, measuring their responses, both what they said about the rubber hand in terms of did it feel like them, and some other measures as well we call proprioceptive drift. We also measured how hypnotizable they are using a 5-point scale. Now, we're all hypnotizable to some degree. It's a stable psychological trait. And the idea we were testing here was that the rubber hand illusion sets up very strong expectations. In psychology, we call them demand characteristics, very strong expectations about what you should experience as a participant. I mean, you see a rubber hand in front of you, you see somebody stroking it, and then you're asked, does it feel like your hand, or something like that? And so, of course, there's an implicit expectation to have that experience. And the hypothesis that Pete and the rest of us had was that that expectation is driving the experience. And if that's true, then it would show up more in people who are highly hypnotizable than those who are not so hypnotizable. Being hypnotizable here, in general, the idea is it makes us more susceptible to these demand characteristics. And that's exactly what we found. There was a strong correlation between hypnotizability and the strength of the rubber hand illusion. This was fascinating, but it has a wider relevance, which is why I wanted to mention it now. Turns out it's not limited to the rubber hand illusion. We see these strong correlations in all sorts of other things too, like this phenomenon called AMSR, the autonomic median sensory response, people having pleasant feelings when observing things like other people folding handkerchiefs. We see it in something called the visually evoked auditory response, where people claim to hear things for images like this, where there's a pylon repeatedly hitting the ground. But we don't see correlations in some basic visual illusions like the Muller-Lyer illusion, where these two lines look different lengths, but they are the same length. So there are some contexts where demand characteristics and expectations change our experience, and others where they don't. Now, this has a lot of implications. For instance, in various therapies, people are using virtual reality as therapy for things like PTSD, for things like pain relief after burn, and many other contexts too. And it could be that these therapies will work very effectively for those highly hypnotizable people, but won't work very well at all for people who are low on the hypnotizability scale. So I think there are therapeutic implications here. There's also a lot of implications for psychology in general, that demand characteristics, this idea of how the experimental setup might influence what people say, what they report, and what they experience. Now, these must be controlled for if we're going to make claims about other kinds of mechanisms. And people have tended to forget about this a bit as we've got carried away with fancy new brain imaging methods and so on. So there's a strong lesson here to go back to some of the basics and make sure that we understand what the context is doing in terms of how it might shape people's responses and behavior, and shape them differently depending on how hypnotizable they are. Okay, enough about having a body. Moving on to being a body, this is where I think self really begins. Beneath personal identity, beneath first-person perspective, even beneath the experience of what is the body, there's this basic experience, layer of experience of emotion and mood, and of simply being a living organism. So what accounts for that? Well, this brings up a whole new realm of perception, which is called interoception. Interoception is the sense of the body from within compared to exteroception, which are all the classic sensory modalities that are open to the world. Now, from the brain's perspective, the interior of the body, which is, of course, critical. I mean, that's what brains are for, fundamentally. They're not uh, for speaking or for being smart. They're for keeping the body and therefore itself alive. Now, the interior of the body is also only accessible indirectly by the brain. The brain needs to make its best guesses about the causes of sensory signals that it's getting from the heart, from the lungs, from the viscera, from the internal physiological milieu in general. This is interoception, the sense of the internal physiological condition of the body. And the claim here is that it's the same principle that applies. Instead of the brain just reading out how the body is in this bottom-up direction, the brain is continuously making predictions about the causes of sensory signals. And the experience of emotion, mood, and just being alive, well, that's the content of these interoceptive predictions in this process of interoceptive inference. This puts a modern gloss on an old idea, in this case from William James, who was one of the first people, along with Karl Lange, to talk about emotion as a perception of the interior of the body. As he put it, bodily changes follow directly the perception of the exciting fact. And that our feeling of the same changes as they occur is the emotion. Now, this is in very Victorian language, but really what he's saying here is that emotions don't follow, emotions don't drive how our physiology responds. They follow, they arise in the act of the brain perceiving the body being in a particular state. If we see a bear running towards us, it's not that the fear causes us to run away, it's that the brain's perception of the body in a state of running away constitutes the fear. So this modern gloss on James's old idea we can call interoceptive inference, the idea that emotion is the content of predictions about interoceptive signals. Now, there's a key aspect to interoceptive inference, which is a bit different from how we were thinking about visual perception. Firstly, this dance of prediction and prediction error is now happening entirely within the body rather than between the brain and the world. But secondly, interoceptive predictions are about controlling things rather than finding things out. The brain doesn't care where the lungs are or what shape they are or what color the stomach is, or really whether it's moving. What it cares about is how well the brain is doing at keeping the body alive. So are the physiological variables like heart rate, blood pressure, and so on, are they within the ranges and likely to remain within the ranges that are compatible with survival? And here's, I think, the key insight here is that being able to make predictions about the causes of signals is a very good basis for being able to proactively regulate and control these signals. Prediction is a beautiful way of enacting control, and especially of maintaining things within desired ranges, because your predictions can become, if you like, physiological set points. In predictive processing, this idea of the predictive brain, this highlights the idea of active inference, championed most prominently by Carl Friston at UCL. And this is the idea that prediction errors can be minimized both by updating the brain's predictions, but also by making actions to change the data so that the predictions become self-fulfilling. That's active inference, making actions to fulfill predictions. And that's how predictive control can work. There are intellectual legacies for this too, intellectual histories and ancestries for this too, especially in a branch of AI called cybernetics, which was very prominent in the early days of AI, less so now. Cybernetics was all about feedback and control and regulation. And there's a very nice confluence of ideas about how the predictive Bayesian brain can implement what this feedback control oriented view of nervous systems was all about in cybernetics. Now back to consciousness for a second. I think that the core message to hang on to from here is that different kinds of predictions will underpin, explain, if you like, different kinds of experience. Visual predictions here underpin visual perceptual experience. And the brain's making predictions about how things move in a spatial frame. So our visual experiences have that character of objects and spaces between them, movement and so on in a spatial frame. But interoceptive predictions underpin embodied experience. Instead of location, movement, and spatial arrangement, embodied experiences are primarily, or at least based on valence. Things feel good or bad, or varieties on that theme. That's because the relevant predictions here are about control and how well control is going. So different kinds of predictions, different kinds of experiences. And if you think about it, then there's a line to be drawn between all of these different ways of experiencing. And they're all fundamentally grounded in this view, in the role of the brain in controlling and regulating the body. If we think what brains were originally for, again, the primary role of a brain for each of us now, but also over evolutionary and developmental history, is to keep the body alive. So in this view, the predictive machinery that underpins all of our experiences, whether of the self or the world, all have their origin, all have their root in this primary biological imperative to stay alive, to keep the body alive. And if you pull on this thread long enough, then you see this intimate connection between our conscious experience and our nature as living creatures. This imperative to stay alive, it drills down even into individual cells, into the metabolic integrity of the building blocks of our physiology. So what we see here is that life is not just something that provides some kind of power to these meat-based computers in our heads. No, life is fundamental to our experiences of the world and the self. And this is also not really a consensus view. Now, many centuries ago, René Descartes was very keen to separate life from mind. He said about other animals, about non-human animals, that without minds to direct their bodily movements, animals must be regarded as unthinking, unfeeling machines that move like clockwork. He called them beast machines, or bête machine in the French. In this view, life and mind are very separate. Animals' status as living creatures is irrelevant to whether they have mind or consciousness or ethical status at all. And I think almost exactly the opposite, because of this intimate connection between the predictive brain and physiological integrity and life and metabolism itself, that we perceive the world around us and ourselves within it with, through, and because of our living bodies. Now, let me finish in the last few minutes with some implications of this view. Consciousness in other things. I've talked about consciousness in humans for the majority. I want to just widen the view, think about consciousness in other things too. Well, firstly, there's diversity between people. We've already talked about that. But of course, human brains are very different from the brains in other animals too. And a human way of being in the world is just one small region in a vast space of other minds. Consider octopuses, for instance. There's been a lot of attention to octopuses lately, starting with Peter Godfrey Smith's brilliant book called Other Minds. And let's just assume that octopuses are conscious. I don't think there's any reason to deny them that privilege. Now, the way of being an octopus is going to be very different from how a human being experiences the world. Octopuses, for example, have more neurons in their arms considered together than in their central brain. So whereas we humans, we just generally know where our body is in space, where our limbs are in space. For an octopus, there may be no such thing. Octopuses might experience themselves as a kind of moving cloud of some sort. It's very hard to know. And it's very interesting to consider this, not only because of the light it might shed on what it is like to be an octopus, but because it reveals the assumptions we might make about our own human experience that could be otherwise. And what we think of as fundamental to consciousness may just be contingent on the particular way in which human bodies have evolved. So there's a vast space of other minds. Unclear quite what the distribution of consciousness is out there in the animal kingdom, whether it's all animals or only some. We can talk about that another time. But another key question, another very timely question, is about artificial intelligence or AI. There's a lot of concern or excitement these days about whether AI is about to become conscious, whether as our language models or other AI systems get smarter, that there'll come a point at which the lights come on and these systems are not only intelligent, but also aware, that they have experiences, that there becomes something it is like to be GPT-5 or GPT-10. Now, I have a lot of skepticism about the possibility and about the desirability of conscious artificial intelligence. The skepticism comes from a few angles. Firstly, consciousness and intelligence are very different things. I mean, we humans, we tend to associate them because we have this residual human exceptionalism. We think we're smart and we know we're conscious, so we put the two together. But really, although intelligence gives us different ways of being conscious, intelligence is about broadly doing the right thing at the right time, and consciousness is about having a feeling. The most basic kinds of conscious experiences like fear, pleasure, disgust may not require much species-level intelligence at all. Even something like GPT is actually not very intelligent and is certainly, in my view anyway, not conscious, even though it might give a very good impression of being so. So consciousness is not just going to come along for the ride as systems get more intelligent. Intelligence and consciousness are different. Now, this is related to two fundamental biases that shape how we think about consciousness in other systems, whether they're other animals or AI systems or other things too. The first is anthropocentrism, the tendency we have to interpret everything through a human-specific lens where the human way of being is at the center of everything, at the top of every pyramid. And again, because we tend to prioritize those things we think of as distinctively human, intelligence, language, and so on, we tend to think of those as also important for other things like consciousness, where they really may not be. Now, the flip side of anthropocentrism is anthropomorphism. This is the human tendency to project human-like qualities into things that don't have them on the basis of superficial similarities. We see this, for example, with language models. They speak a little bit like us, so we project understanding mind and sometimes even consciousness into these language models. Now, these two biases can lead us to make errors. Anthropocentrism can lead us to not attribute consciousness to things that may have consciousness, maybe other animals that have very different form to us. And anthropomorphism can lead us to attribute consciousness wrongly to things that don't have them, like language models. And we need to recognize the impact that these biases have. There's also a more fundamental reason why I think conscious AI is unlikely, which is that brains are not computers. The metaphor of a computer has been very useful, but wetware is very different from hardware. And one critical difference between wetware and hardware is that in the computer, there's a very sharp distinction between the software, the program that a computer runs, and the hardware, the silicon that's doing the running of the program. But in a brain, we do not have this kind of sharp separation between the mindware and the wetware. Even single neurons are maintaining their integrity as they go about their business of firing. And every time a neuron fires, the structure of the surrounding neurons changes. So it's not even clear that we can think of the brain as something that implements an algorithm in the same way that computers implement algorithms. So if consciousness is a property of living systems only, then it's not something a computer could have, even though computers can give us that strong impression, again, of having it. And this brings me to my last point, which is that we shouldn't even want conscious AI. If we did develop conscious computers, we would have introduced vast new opportunities for suffering, potentially. Could be an ethical catastrophe on an industrial scale. But I think conscious AI is very far away. However, there are also dangers in artificial intelligence that merely seems to be conscious. And we're almost there already. And some people already think that language models are conscious, and certainly if they're also coupled with deep fake videos, then we're going to be living in a world where it will be almost impossible, or perhaps impossible, to resist attributing consciousness to AI systems that don't actually have any consciousness at all. In the same way that we can't help see these two lines as being different lengths, even though we know they're the same length. The illusion of conscious AI might be cognitively impenetrable in exactly this sense. And this will be problematic because we're left with two choices about how we respond to systems in this very near-term world. One is that we learn to we decide to care about these systems even though we know that they are not conscious. And in that case, we might sacrifice human interests in the competing interests of hunks of silicon and code that feel nothing at all. The alternative is what I like to call the Westworld problem, which is why the image is here, which is that we learn to not care about these things, even though they seem conscious. And this can be brutalizing for our psychology. This is what happens in Westworld. People learn to treat badly these humanoid robots that behave as if they are aware and have feelings, but probably don't. This idea of brutalizing our psychology goes back to Kant, and it's very, very unhealthy for our minds to treat things as if they have no feelings when they give us the strong impression that they do. So there are no answers to this here, but just a call that we need to think very carefully about how we develop these kinds of technologies, given their potential impact on our society and on our psychologies. There are other things to worry about too, I think. Much more likely than conscious AI are things like conscious brain organoids, these mini brains created in the laboratory. Now, they're made of neurons. They don't do anything, not much anyway. So they don't exercise our anthropomorphic projections, but they're made out of the same stuff. So a whole level of ambiguity about whether the stuff matters for consciousness goes away. I wrote about this recently in a paper called Islands of Awareness. Here are some organoids, and recent experiments have shown that these organoids can actually begin to control things as well. So maybe once organoids are hooked up to a world, things get even more complicated. So there is the possibility of synthetic consciousness, but I think it's going to be more likely in biotechnology than in AI. I'll finish with Frankenstein. Frankenstein is a wonderful book. I read it surprisingly for me for the first time last year. I thought I'd read it before. And I want to finish with it because it has a message which I think is increasingly relevant today. Now, when most people think about Frankenstein, they think, or I think the main general moral taken is that it's a message about the hubris of creating life, of giving life to something that didn't have it. But reading it now, that's not the message I take. In Frankenstein, all the bad things that happened, all the carnage, all the disaster, was a consequence not of the fact that Frankenstein's creature was alive, but that it could feel, that it was conscious, that it experienced resentment and envy and ostracism and misery. Without consciousness, then there would be no story. So I think the moral message of Frankenstein for today is that we should be very careful about consciousness. We should value our own and its diversity and individuality, its presence in other species as well, beyond the human. But we should also be very careful about attempts to create consciousness in AI, or even create systems that give the appearance of consciousness, because these systems will bring with them ethical consequences that I do not think as a society we are well prepared for. Thank you very much. With that, I'll finish. The work I presented throughout the lecture has been in collaboration with many people in my lab at Sussex and beyond, so I want to thank them all. And I will leave you just with a flyer for a recent book on consciousness, which explores all these issues and many more. Thank you very much.